Okay, so we will continue with the remaining stability check for the mud mat type of foundation. We have seen this previously. The sliding stability is just by means of drained condition where the friction factor between the mud mat and the soil is taken as the resistance. So basically you can see this particular formula or the methodology does not relate to the mud mat area. You can see this weight plays a major role and the friction factor which is independent of the surface area of the foundation. You know, like if you have a larger or smaller does not matter. So you can see here is mu is predominantly is a surface area parameter, but does not really account for the larger or smaller extent of mud mat. This is basically the drained condition which we you could use it in areas where the drained condition do exist, and even in undrained condition many cases for sandy material we use this type of calculation. Whereas API suggests if you have a clayey surface of the mud mat surface area, many of the places you will see that sediments. So you should use this particular concept of multiplying undrained shear strength with the area of the mud mat, which is going to give you the the resistance against sliding divided by the total. So basic formulation is drained versus undrained condition, and again the factor safety is supposed to be 1.5. Now API also suggests in the recent revision, earlier we used to have a RP2A which is combined code, includes structure and foundation. The last 2-3 years back they have removed the geotechnical portion, and separately a code has been revised and introduced which is called API RP2 Geo, which includes almost all aspects of foundation design including piles and mud mat. This has come into effect only last year, and basically you can see they have asked us to incorporate the effect of both the horizontal and vertical load. So when you do this, for example, you have a sliding stability which is predominantly due to horizontal load and bearing stability predominantly due to vertical load, and when you combine them you may actually find an envelope very similar to our unity check when you are studying in your design course. Axial load with bending moment, you can do an interaction ratio, which if you have purely axial load you can take the ratio to 1, and vice versa when you take only the bending moment you can take to 1, and if you have a combined effect you should actually get a very similar to this curve, very similar to the beam column interaction curve. I think we have discussed it in very much detail. So you should combine them with the vertical load and the horizontal load. So the prorated ratio of course is a non-linear, is not a linear, and this curve depends on type of soil and the type of condition. So this is for undrained condition, this is for drained condition. So you could see that we should follow this particular relationship rather than simply checking the vertical bearing capacity and ultimate bearing capacity versus the pressure, and you decide a factor safety. Not only that, you have to go for associated horizontal load and find out what is the sliding factor safety and then combine them, which seems to be reasonably correct, because ultimately when you look at overturning stability it includes the vertical load as well as the horizontal load. So even if the bearing capacity and the factor safety is safe, still the jacket can be very much unstable against overturning. So that is why this combined horizontal and vertical stability needs to be reviewed, so that the systems as a whole is safe. The next thing what we need to find out is, when you have a soft material, most of the places you will see that the mud floor, at least for first few meters, 2 meters, 3 meters, in some cases maybe a deeper depth like 10 meters, 15 meters will be very soft, may not actually give sufficient capacity to restrain the jacket from settlement. So what we need to really review is how much settlement is actually acceptable to us, whether it is few millimeter or few hundred millimeters, and basically it depends on several parameters at the interface. If the jacket settles by too much, one of the important interface between the jacket and the top sides will change. So if you are not prepared for it, you have not taken adequate measures to adjust that level, will actually make the platform unusable. That is why If it is by few hundred millimeters, you can adjust, but if it goes down by few meters, then it may be too much to accommodate. So, that is why we need to have an assessment done on the temporary time that before piling and after the placement of the jacket on the mud line, how much is the immediate settlement happening, and most of the thing the settlement will be instantaneous, even if it is clayey type of soil, because once the settlement happens, you are going to do piling, you are not allowing consolidation settlement for several years, because already the jacket will be resting or in fact supported on the piles. So, what we are looking at is not the time bound settlement, the settlement happens instantaneously immediately after the placement of the jacket, which can easily be found by the means of elastic formulas. If you see, this formula is basically loading times the width for a rectangular or strip footing multiplied by 1 minus mu square by E, which is a simple elastic expression, except that this IS is just to account for the shape of the foundation, which I think we discussed during our earlier bearing capacity. So, that is what is the idea behind that. We want to find out the settlement of the total jacket due to not only the vertical load, but also due to horizontal load, because this could introduce increased pressure on one side, which could make the jacket, instead of vertically going down, it may actually try to tilt. So, what we need to find out is what is the average bearing pressure on this area and see how much is settling here, and similarly here. So, you could see that jacket could actually give a little bit of problem on inclination. So, you may actually have to do a leveling of the jacket, normally it is done after the placement. So, what are the causes of this type of settlement is, one of them is jacket cutoff will be affected, the level which you planned, so that you can put the top sides. If it is settled by half a meter, then you need to bring in additional structural steel and then weld it, so that the deck levels will be maintained. You can see here the conductors support framing can go into mud line. So, when you are inserting a conductor, you do not know where it is unless you excavate the soil. So, these are some of the effects that you do not want. So, you want to prevent it from happening. That is why the amount of settlement, if it can be estimated, so that you make everything pre-arranged, so that even after 500 mm settlement your requirements are met. So, that is the idea behind, but at the same time you should not overestimate. Instead of lesser settlement happening in the field, you estimate higher than the actual, you are actually going to produce different problems. So, this actually you need to find a solution within upper and lower bound. What could be the maximum expected settlement, what could be the minimum expected settlement, within which you can play your parameters such that the ultimate requirements are not actually giving into a problem. So, this is the simplest formula that we normally use for estimation of settlement. Q is the applied pressure. It could be peak pressure if you want to find out one point displacement, or it could be an average pressure in an area. If you have a mud mat, like a 4 corner mud mats of say typically one rectangular or square shape. So, you find out the average pressure in that corner and use that, or it could be a peak pressure at one particular location in the overall system multiplied by the width in that location. So, if you have a rectangular strip in that particular corner, that will be your B divided by E, and 1 minus mu square, mu is your Poisson ratio of the soil, and IS is the influence coefficient, which I think if you remember we have discussed about these parameters. IS is a function of F1, F2, and then you can go and find out F1 and F2 depending on depth of embedment and also the shape of the mud mat area, whether it is rectangular L by B ratio. So, you could find out this effect of influence of the shape and the location of the mud mat with respect to the mud line, multiply, normally it should be less than 1. API also suggests an alternative formula, instead of using this E values and mu value, slightly modified formula. Basically, Q is the vertical load, this is for a particular corner. You know, if you look at 4 legs, you have 4 mud mat shapes of any kind. So, you can take that and basically convert it into an equivalent circular shape. It can be triangular or rectangular or other odd shapes. In some cases, we do have cases where mud mat will not be rectangular, it could be combining the skirt sleeve. I think I have shown you some photographs, photo or not the pictures showing combining main leg with the skirt sleeve, which will not be of any particular shape. So, you can convert that into a equivalent circular base and then use it in this formula, which will produce similar result. In fact, you can derive this from here or vice versa, and G is the elastic shear modulus and Q is the total vertical load, not the unit pressure, and then the vertical displacement also can be calculated. Now, I will just introduce a few slides showing various formulas that you will require for solving MUDMAT problems, which you should be able to understand, do not have to memorize, and will not be given in the exam. So, you should be able to derive it yourself for various systems of MUDMAT area. So, if you look at this is a rectangular area, and what we are looking at is overall system pressure calculation. You need to find out the moment of inertia with respect to this point, because we are treating this as one unit rigid body and trying to produce vertical pressure due to vertical load as well as horizontal load. The picture something like this, something like this. So, what we are looking at is the pressure at this point, pressure at this point, or on various points along the periphery as well as any other intermediate points. So, if you look at the equation for calculating the pressure is W by A, which is A is the 4 times the individual areas. Individual area is B times H, very simple idea. And then the Ix Iy is about the axis of rotation, which is Xx and Yy. So, we are just taking the independent or the self moment of inertia plus area times square from the axis of consideration, whether it is x axis or y axis. So, you need to remember to derive. If it is a complex shape, you should be able to derive it in 2 minutes. So, that is the main thing that you have to remember, and do not ask for formulas of. So, this particular one is very easy, because PHQ by 12 you must be remembering all the time, and area times distance square from here to the center of that area, which actually represent that the whole system. So, if you are looking at a pressure at this point, you will take P by A, which is very simple, plus due to Xx and Yy contributions, you will look at what are the forces acting on the x direction and y direction, corresponding moment of inertia you calculate, and then multiply by the distance from here to the point of consideration. It is not that always h by 2 or you have, if you are looking at a pressure at this point, you have to multiply by the distance from here to the point of whichever the point. So, you will just put a notations accordingly, which I think will be easier. Similarly, you see the circular one, which is the concept must be same. If you look at this, is the self moment of inertia 4 times because of 4 corners, plus area 4 times multiplied by your distance square from the new centroidal axis to the centroid of the particular. So, similar principle you can easily apply, and any shapes you can derive it without much problem. This is for circular and for triangular, and then the last one is for triangular jacket with triangular MUDMAT. So, all these you must remember to or learn to derive. I think you should have studied in your mechanics course of any complex shape. The next we want to see one example problem. This is a particular simple problem where a jacket is subjected to the horizontal forces of this magnitude at this centroid from the base of this jacket or from the mud line, and the weight of the jacket is this much. Center of gravity is minus 6 meter and 1 meter. So, you are given the data to determine, find out the bearing capacity. Basically, the soil data is given here, dimensions are given here. So, you can see here everything is given, find out the factor of safety against bearing, that means the vertical equilibrium and sliding and overturning. And you see here the jacket weight is 12,000 kilonewton. This is the typical case. Most of the cases, if you have a 2000 tons weight of the jacket in air during transportation or load out, you will see that the weight of the jacket at the time of placement inside water will be about 50%, sometimes less than 50%. We have compartments we have jacket, most of them are buoyant at the time of just launching or lifting. Once you place, you will make the jacket heavier than otherwise it will not be able to sit on the seabed. So, you will make it heavier, but not all the time that you make it full heavier to the weight of the jacket in air or during transportation. So, you will make it slightly heavier, so that it will still sit and stable, so that you will be able to do the pile driving. Mostly you will be able to see that many of the jackets, almost 50% of the dry weight, that is what the normal idea you will get it. Some cases it may be slightly less, especially bigger jackets, like if it is a 10,000 ton jacket, we do not want to make it as big as 5,000, maybe 2,000 or 3,000. So, in this particular case, this is actually a 2,500 ton jacket. So, you can see it is almost half the weight, but the COG is a bigger problem. You can see the COG is shifting by 6 meters towards one direction, which is what is going to cause bigger problem. So, we need to bring the COG back. In many cases, when the COG is on one side, for example, in this case the COG is on the vertical face side, it is moving towards. How do we actually encounter this type of situation? If the COG is giving a lot of trouble, we can actually bring back the COG by attaching artificial weights, as long as you have the capacity to do launching or lifting. For example, before launching you can attach some kind of heavy weight, a pipe filled with concrete, and later you can remove it. Sometimes we do this type of manipulation, but normally not preferred, because this involves additional offshore work to remove. So, permanent design, without doing any much implementation of additional measures for shifting the COG, you design the mud mat system to encounter such type of COG. So, you can see here COG is shifting towards the west and the north side. So, what we need to see is what this will be the point of consideration of importance, because that is where you are going to see the pressure is going to be more. So, all our problem will be associated with this corner. Now, within this corner you can see there are 4 points, and you know very well point number 4 is going to give you the highest bearing pressure, number 1, and the rotational instability will be with respect to either 1 or with respect to B, because it is going to rotate either that side or this side, depending on what will be the magnitude of forces. But fortunately you can see here we have got forces given for this direction and this direction. Now, you need to wonder, before you start wasting your time in doing unnecessary calculations, you need to see which will be the critical one, and that is what you have to evaluate in at least in the examination point of view. If you are given a problem like this, which one I should work out so that I can get the minimum or the maximum factor of safety or minimum factor of safety, depending on which phase is critical. So, which you can actually evaluate. Center of gravity is moving towards this direction, and you can see here this is the phase that is going to cause instability, because COG is on this side. Similarly, the COG is on that side, maybe, but all depends on whether the magnitude of force is more here or more here. Now, here there is no force is given, so you are given only. So, there is no reason why you should actually waste time in doing this, using this force, trying to find out what is the factor of safety, unless the magnitude of this is very large compared to this, because the component of this also will come into this direction. So, you should do a due diligence before attempting to solve the problem. Some of the problem may be very difficult. So, in that case you will be able to just do it and then decide. Some of the problem, by screening itself you can see you do not need to do all other things, you can just do. So, you should employ your intelligence in doing this, so that you can reduce the time. In this particular case, the width of the jacket is 40 meters, and the other dimension or the length of the jacket is 50 meters between A and B, and the individual dimension of the mud mats are given 10 meter by 10 meter, which is squarish. And the load application, you can see here the heights are given y3, y1, and basically the other one is not visible here. Basically, if you go back to this picture, the center of force from the mud line, always these wave or environmental forces will be given from the mud line, and the magnitudes are given. The directions are given by the diagrammatic arrangement. So, you have every parameter. So, we just need to solve for it, and also the weight of the jacket is given as 12,000 kilonewton. So, we will just quickly look at this, but then in the tutorial we can solve for a bit more complicated problem. So, the material of the seabed is soft clay and simplistic is 20 kPa is the undrained shear strength, and the density is 16 kilonewton per cubic meter. So, you have the parameter to evaluate your bearing capacity. Since this is being a clay type of soil, I think you can use your simple bearing capacity formula to arrive at, and you can use that. And the mud mat is always going to be sitting on seabed, that means the depth of foundation is going to be 0. Initially it is going to sit on the mud mat, is on the mud line itself. Later what will happen, as the jacket settles down, it will find its own equilibrium after settling say few hundred millimeters. So, that much, but initial calculation of bearing capacity you should use d is equal to 0, because that is how we start with, and later if you are asked to find out the settlement, then find out the settlement, then use that as the depth of the foundation to go and increase your bearing capacity, which is the second step. Right now in this problem I have not asked you to go there, it is simply finding out the factor of safety against bearing, sliding and overturning. So, in this case the procedure is quite simple, I think, is because square mud mat, area, width times the other dimension, which is 100 meter square, 4 times, and then you have Ix, Iy of the individual mud mats, and then the combined system moment of inertia, which is, and then what we are just doing here in this particular case I have just wanted to show you was, I describe all these points. If you go back to the picture, each one of the point is given an xy coordinate with respect to the center of the system, geometric center of the system. So, this dot point what I have put here is basically the origin of the overall mud mat system. So, if you look at number 1, you can assign an x and y coordinate based on this origin. This will be minus 20 meter and minus 25 meters. Once you assign xy coordinates, it is easy to calculate using the formula for, so that is where I have just, so from all the points, point number 1 all the way up to point number 16, you can assign coordinates for finding out the x component of the pressure and y component of the pressure from various, this is just an automated procedure. And then you describe all your forces, for all, if you look at number of cases, is one is the dead load case, the other one is 3 horizontal load applied in 3 different directions, just to automate, otherwise there is nothing. So, you have F1, F2, F3, and then W is your vertical load of the jacket, which is taken in the negative direction. The remaining you take the directions according to and resolve the components accordingly. Basically for this particular case, this one is resolved in x direction as well as in y direction, so that you can combine them, but F1 and F2 are not going to be concurrent, they will be applied in a different timing. So, maybe wave is coming in this direction for some time and wave is having another direction. So, you should not combine F1 and F2. F2 may contribute in this x direction a bigger force if the magnitude is larger at that time. So, you will be having whether F1 is governing or F2 is governing, we will not be knowing unless you do a simple resolution of force and find out what is the component of F2 in x direction or in y direction. In any case, if it is in y direction component more, you are not going to have much problem, because you see the COG is on that side and may actually help you. So, that is what is done in this particular example, and then using this formula, the vertical load divided by the area and then corresponding the moment produced by horizontal load and divided by the moment of inertia into the coordinate of interest. So, it is just various coordinates are all the 15 coordinates already we have assigned for each and every point. So, you can just simply find out. So, this is the matrix of pressure, the total pressure applied by the jacket and the environmental load. So, it is just various loads and various points. Just look at around, you can see here one of them is going to be maximum, so maybe 55, maybe I think is 55 is maximum at point number 15 and 50, 43. So, what we are looking at is in this diagram where is the maximum pressure occurring, we want to find out whether it is 15 or I think 4 and take that and compare it with the ultimate bearing capacity. So, if you look at the ultimate bearing capacity, you can easily calculate using your bearing capacity formulas. This full formula is expressed here. Of course, substitution of parameters here, phi is equal to 0 because it is clay, and you get a allowable bearing capacity after dividing by the factor of safety, or in fact ultimate bearing capacity. Then you can later divide by the factor, it should be ultimate. It is not yet divided by the factor of safety here, because still you are using the shape factor and the depth factor and the basic CU. NC is calculated, but ultimately you will get 5.12, which I think we derived earlier. So, you take the maximum bearing pressure for dead load case among the 16 points, so which is about 47, and maximum bearing pressure including the wave effect, which is actually for the last 3 load cases. So, you can see here the bearing capacity, this is ultimate divided by the applied pressure, gives you the factor of safety of 2.6, which we require a factor of safety of 2 minimum. And then similarly for the overall maximum applied pressure is 59.4. I think if you look at somewhere it is there, 59.4 is here, point number 2, point number 1 at load case 2. So, you can take that divided by the bearing capacity divided by the applied pressure, you get the factor of safety of 2, which is slightly higher than 1.5. So, it is not a problem. Similarly, you should be able to do a sliding check and the overturning check, and sliding check is very easy. Basic the loads are available. So, what you need is the frictional resistance between the mud mat and the soil. So, one of the important things that you need to understand in the overturning check about which phase you want to do the rotational instability. We will just go back to this picture, the elevation picture, or in fact that picture will be easy to understand. So, if you are looking at this instability about the line along the vertical phase, for example, because of the environmental load here, the overturning moment is F times H, which is going to cause the instability in rotation. The moment that actually keeps the jacket in vertical position is the distance x multiplied by W. Now, for example, if the center of gravity keep moving towards the phase which is vertical phase, which is what we are worried about instability, which is going to cause lesser factor of safety. So, the distance x is more important. So, every time when you are evaluating the rotational instability about a particular phase, you need to find out the CG of the system with respect to that phase. So, as long as you know Ex, you can find out x, because the location of the geometric center of the mud mat is already known to us. So, this Ex will be given. Ex is nothing but your x center of gravity or y center of gravity from the geometric center, and the distance x is of more important. So, if the COG is going towards here, is no good, COG is coming towards the other side, for example, you will have no problem. So, that is where we need to be determining, depending on what is the COG given to us in this diagram. COG is on this side, we know x is minus 6 meter. So, you simply find out what is the distance from grid 1 towards the COG. So, that means the half the width of the jacket, which is 20 meter minus 6, we will get 14 meter. 14 meter multiplied by your weight of the jacket will give you the resisting moment against overturning due to load arising from F1 or from component of F2. So, that is the calculation that we are looking at, and if you want to find out rotational instability with respect to F3, you will find out the distance from this COG to grid number 2, which is 20 meter plus 6 meter. So, somehow you have to automate the whole procedure, so that you can easily, we are trying to find out the distances 14 meter or 26 meter or either way, all 4 phases you can find out, phase 1, phase 2, phase 3, phase 4 with respect to the COG, what is the distance, so that the multiplication can automatically be done. So, basically the factor of safety is calculated here resisting moment divided by applied moment. So, resisting moment is weight of the jacket multiplied by the distance to that face. So, that is the calculations, and factor of safety seems to be very high. So, no issues. So, one important observation, if you go back to this particular table, you will be able to determine whether overturning stability will be a problem or not. At any time, if the values are becoming negative, then there is a worry. That means, the jacket is not full contact at the interface. So, you see here the minimum bearing pressure is about 4.2, I think is 4.2. So, still there is a contact of mud mat between mud mat and the soil, because the bearing pressure is still positive. Once it becomes 0 or negative, that means the jacket is almost about in the instability in rotation, or it may be just already failed. So, that is the idea behind. So, once you get the bearing pressure, the first thing you need to find out is whether any point is having negative bearing pressure. That is why, though we do not actually need to find out any of the points, because we know if it is this point is going to be critical, you just find out and then find out the factor of safety, but it is obvious that you better look at all the points and see whether any negative pressure is coming. If negative pressure is coming, for example, in point number 1 or point number 13, then some of the areas are not effectively participating in the system. So, you have to detect that area and adjust it. That means, the moment of inertia calculation what we have got just now is not valid, because not full mud mat area is participating in the combined effect of vertical and the horizontal loads. So, you will see that some area is reduced, then change this formula accordingly and recalculate the moment of inertia, and then recalculate the bearing pressure and then check, which will be a little bit of a complex procedure, because once you reduce again it will be shifting. So, you may require several iterations before you get an equilibrium. So, overturning is basically a simple idea, but you will find 4 faces or 4 edges, I would say, not faces. So, in this particular case we have got the 4 edges to check, and has been done. Sliding stability, in this particular case we want to find out using a friction coefficient of 0.45. I am not very sure it was given in the problem, I think it was not given. So, for a clay type of soil, typically the friction factor between the steel, mud mat and most of the clay material varies from 0.3 to 0.6, and in this particular case I have assumed 0.45 as the friction factor, and then you could also check using the undrained condition and check using drained condition. You could find whichever is governing. Mostly we will use it in practical applications. For examination point of view, I think you should be using undrained condition, and will be given which condition to use. So, I think something is missing here, but in any case the sliding factor safety is also coming more than 1.5 what is required.